On this slide, we consider a function which will have a discontinuity at point 0. So consider a function of the form fx equals to x square for x not equal to 0. That is, it is a normal parabola except at point 0, and at point 0 we give it a value of minus half or minus 0.5. So this is how the function looks like. So we do not have the point 0, 0 on the parabola here. So therefore I write it as undefined at point 0, 0. So when x is 0, we give it a value of minus 0.5, which is marked in blue. So consider a point x comma fx on the parabola. So say you have x comma x square because fx is x square. We want to determine limit at point 0. So you can approach 0 from the positive side, or you could approach 0 from the negative side. Right now I'm approaching 0 from the negative side. So you see, if you approach from the positive side or the negative side, the limit is 0. So first you see, if you approach from the negative side, the limit is 0. If you approach from the positive side, that is from values higher than 0, you approach 0 from values higher than 0, you still get f of x as 0. So let us see this more graphically. So we start approaching from the negative side first, that is from values less than 0. So as you see, as the x coordinate gets closer and closer to 0, f of x, which is x square, also gets closer and closer to 0. So therefore limit of x tends to 0 from the negative side, f of x is 0. Now again we do it from the positive side. Now we are approaching 0 from the positive side. So we are saying limit of x tends to 0 from the positive side, f of x. So as you see, as we get closer and closer to 0, f of x also becomes 0. So since the limit from the negative side and the limit from the positive side both agree, we say limit exists as x tends to 0, and this limit is nothing but 0. So limit x tends to 0, f of x is 0. Now notice that the value of f of 0, that is when x is equal to 0, is minus 0.5. Thus f of 0 is not equal to the limit when x tends to 0. So you cannot just plug in the value 0 and say that f of 0 is the limit. As you see, f of 0 is minus 0.5 here and the limit is 0. So you have a limit, but it is not equal to the f of 0. So this is important. You have a limit, but as x tends to 0, but it is not equal to f of 0. Now consider another function of this form. F of x over x square minus x minus 1 divided by x cube minus 3x square plus 2x. Now immediately notice the first fraction, x minus 2 divided by x square minus x. The denominator is 0 at x equals to 1. So the first fraction is not defined at 1. Similarly, in the second case, if you put 1 for x, that is x cube minus 3x square plus 2x, is again not defined at 1. So this is how the graph of this function f of x looks like. As I said before, it is not defined at x equals to 1 because both the fractions are not defined at x equals to 1. Now we want to find the limit as x tends to 1. So as you see, if you are going towards 1 from the negative side, you get see f of x is 2. If you go to 1 from the positive side, again you see f of x is 2. I've put this point in blue. So now we are seeing as you are going towards x tends to 1, you can see f of x is becoming 2. Now x tends to 1, from the negative side, f of x is becoming 2. And at 1, it is not defined. Similarly, when you approach from the positive side, you can see as you approach 1 from the positive side, you can see f of x is also becoming 2. So you can see as we get closer and closer, it becomes 2. So later on, we will learn how to solve such kind of limits algebraically. Right now, we are just seeing it in the form of a figure. So let us write down the observations we have just made. We have seen if you approach from the negative side of 1, you get 2. And this is the same if you approach x or when x tends to 1 from the positive side, that is from the number slightly greater than number 1, you again get 2 as we just saw. Now since these two limits agree, that is if you tend to x from numbers less than 1 or x tends to 1 from numbers slightly more than 1, both give value 2. Therefore, the limit exists at 1 and this limit is given as 2. But notice that f of 1 is not even defined here. F of 1 is not even defined, but we have a limit when x tends to 1.